Hi everybody, welcome back to another episode of Phys 4250 or 8250, Design and Application of Lasers. I'm your instructor, Dr. TJ Hammond. This week, starting Monday, October 5th, we'll be covering Chapter 5 from your textbook, Laser Oscillation, Power and Frequency. I don't know if I can have enough colons in my titles, but that's how I have it set up. So, what are we covering in Chapter 5? Or why are we covering Chapter 5? So up to now, we've been talking about the intensity or the photon flux that's inside the laser cavity. So we've been talking about gain, we've been talking about the transmission, the reflection of the mirrors. But the thing is, we actually want to use the laser for something, right? You push the button to your laser pointer and you want to shine this laser across the room, or you have this laser that you want to shine on some experiment. You don't put the experiment inside the laser. The experiment is outside the laser. So we need something some of this light to be coming out of this laser. So this week, what we're going to be understanding is how to get that light out of the laser cavity and what that means, how we can optimize that power, how we can tune those frequencies. That's what we're going to be trying to do this week. So this week on Monday, we'll be covering sections 5.1 to 5.3. So this is using the uniform field approximation and optimizing the output coupling, so optimizing that power that comes out of the laser. On Wednesday, we'll be covering sections 5.9 to 5.11. So that's talking about frequency pulling, single mode oscillation, and line width. So that's going to discuss how to get this, how to select the frequency out of the laser and what that takes depending on the gain medium and what your and the configuration of your laser cavity. On Friday, we'll be talking about the Fabry-Perot etalon, which will be related to the stuff that we talked about on Wednesday, and we'll be discussing laser at threshold. Because we've been talking about threshold gain, we're going to talk about laser at threshold. So the daily assignment is that when we go through this derivation for optimal coupling, we've included S, the scattering coefficient, in our laser. Why do we need to have it now? Why didn't we have it before? What could account for S? So what could be instances of causing scattering? Is this going to be from what part of the laser, I guess, is going to be causing these scattering events? So think of the laser setup, okay? And that is this laser setup. Okay, so we're going to be covering this lecture, uniform field approximation. So what we're going to assume is that the reflectivity of this mirror here is very high, and the reflectivity of this mirror is also very high. In fact, we're going to assume that the reflectivity of this mirror is 1, and this one is very close to 1. And we're also going to assume that the gain per pass isn't very high. So what that means is some photons bounce around here. They increase in number, but not a significant number compared to the ones we already have. It hits this output coupler. Some of these photons then leave this laser, and we can shine on our experiment or shine across the room. But only a few of them escape. Most of them get reflected. So the difference between I plus and I minus here isn't significant. Then, of course, these photons get amplified here, but this amplification isn't very much. So say if we have, so if you remember from one of the earlier assignments, how many photons do we have in I think a 1 milliwatt beam, and it's something like 10 to the 15 photons. Well, imagine we have, say, 10 to the 15 photons, and then we add, say, even, a billion photons as we propagate through this gain material. Well, a billion photons is 10 to the 9, and so we have 6 orders of magnitude more photons here than we've added here. And so it's a small fractional increase per pass, okay? So that's basically the assumption of this uniform field approximation. Obviously, it's an approximation. There's a more complicated derivation if we don't use the uniform field approximation and if this output coupler is large output coupling. But the math is simplest, and kind of the physical process doesn't really change. So we're just going to use this uniform field approximation. Okay, so that's what the uniform field approximation is. And now we've already shown before that the gain at threshold is going to be -1/2 times the length of this gain medium times the log of R1, which is the reflection coefficient of this guy, times the reflection coefficient of this guy. Now, we've just said that R1 and R2 are very close to 1, and so that means that the log of R1, R2 is very close to negative 1 minus R1 over, or R1 times R2. So it means that the gain at threshold is very close to 1 over 2 times the gain of this, the length of this gain medium times 1 minus R1 R2. And what we saw on Friday was the threshold gain for steady state oscillation. So this was the gain that we had when we had when we were at steady state, which means that our laser intensity wasn't changing as a function of time, but it also meant that our state populations weren't changing as a function of time. Okay, so this gain medium, well, this gain medium, or this gain threshold gain here is just dependent on the length of our gain medium and the losses that are incurred by the reflection of these mirrors, whereas here this gain is this G naught divided by 1 plus I over I saturation. And this is gain medium and photon dependent, okay? So obviously what we're going to be doing is equating these two things and seeing what that means. So I've been getting some comments that I've been showing the derivations basically in the notes, and then I kind of talk about them in class, but you guys don't get to see how the math actually works. I'm going to, I'll take that, that advice into account, and I'm going to go through the math, more handwritten notely. Yeah, so it will take up more time, but hopefully we still get through the material that we need to. So thank you very much for that feedback. Yeah, I will be able to use that for, we'll be able to understand these derivations maybe slightly more clearly. The thing that we'll also be talking about is optimal output coupling, and so the optimal transmission coefficient that we'll have for this output coupler is going to be the square root of 2 times this G naught, this gain, times the length of the gain medium, times the scattering rate minus, or the scattering coefficient minus the scattering coefficient. Where we also have the output of the laser is going to be 1/2 the transmission of this, well, I guess I should say, the output of this is, of course, just the photons traveling to the right times the transmission of this. But we'll be going through this derivation and show that this is 1/2 T2, the transmission coefficient of this guy, times the saturation intensity that we've already seen here, times 2 G naught L, so that's the gain times this laser length, this laser gain length over this transmission plus the scattering coefficient minus 1. So we'll be going through that derivation here, and we'll be understanding this optimal output coupling here. And then we'll be also discussing, well, if this is the optimal output coupling, of course, so this is the, the optimal transmission coefficient, and we have this maximum, we have some, intensity within this cavity. Well, what that's going to lead to is some maximum output intensity. And so that's going to be given by this equation here. And so this output max is going to be approximately equal to this gain G naught times the length of the gain medium times the saturation intensity. And we'll be going through in class what all these terms mean. The conversion efficiency, so this is what we'll be finishing up in class, hopefully on Monday, is how to, what could be the optimum conversion efficiency from our pump to our laser, right? So our pump is given here in green, so we're taking the population from state 1 up to state 3, and then the laser has an output from state 2 down to state 1. So notice that this vertical axis is always energy, and so we're always going to be pumping at a higher energy than will be the laser transition. So these colors actually kind of make sense. We pump at green, so we pump with a certain energy, and then what the laser actually gives out is something of lower energy. So the pump power is going to be absorbed by the ground state atoms is going to depend on this energy from transition from state 1 to state 3, the pumping rate, how hard we're pumping this, so P, and the number of atoms in this state, right? So if we have more atoms in the state, more likely to absorb them. So that means that this pump power is going to be the energy of this transition times that pumping rate times the number of atoms here. Now, this efficiency for this optimal output is going to be this gain times this length over the saturation intensity, right? And so that means the efficiency is going to be the ratio of that case. So we're going to have the gain times the saturation intensity over this pumping power, right? Now, what is this G naught? So if you remember, for 3-level lasers, this G naught was the absorption cross-section, so how likely this photon interacts with this state. And then it's going to be the difference of this pumping rate minus this spontaneous decay rate, so this decay rate without a stimulated emission, divided by the pumping rate plus this transition rate without stimulated emission, so just the spontaneous decay rate, times the total number of atoms that are involved in the system, or molecules, or whatever, or electrons that are involved in this transition. So that means that we substitute this definition of our gain into our efficiency equation, and what we get is that the efficiency is going to be the difference of this pumping rate and the spontaneous decay rate times the energy of this transition here, divided by 2 times the energy of this transition here times the pumping rate, and then it's going to be the ratio of all the atoms divided by the number of atoms in the state. So if we make some further approximations, the most efficient we can possibly be for a 3-level laser is going to be E2 to E1, so that's the energy difference of these 2 states, divided by the energy difference of these 2 states here, okay? That's the most efficient you can possibly be. The textbook gives you some answers, like some numbers to this, and it turns out for a Ruby laser, it's something like 80% is a quantum efficiency, and a YAG laser, which is a common very high power 4-level laser system, is about 50%. So you can see that a 4-level laser is going to be slightly less efficient. So it turns out the answer for a 4-level laser is instead involving the 0th state. And so you have slightly greater energy for the pumping than you have for this transition, and so that decreases that quantum efficiency a little bit. Although previously we were saying that these lasers are more efficient in that you don't have to pump them very hard to get some laser out. It turns out their quantum efficiency, or their ideal efficiency from how much energy you put into the system versus how much energy you extract out of the system, isn't going to be as efficient. Basically, you can imagine that since a 3-level laser has only one of this fast non-radiative decay, that's going to lead to some kind of, say, absorption or scattering of energy, whereas a 4-level laser has a second like fast decay, non-radiative fast decay, and so that's going to further decrease the amount of energy that you have in this laser transition, or the output that you can get from this laser. Now, this is the theoretical maximum, but that's not true at all. If you actually take a pen laser and how much, for like a laser pointer, and how much energy you have to put into that versus how much energy you get out, it turns out to be much less than that. It's more like on the order of 5 to 10%. And that's about as good as you can do with practical systems, just because you have, heating, you have to do, various things that will always cause this to be much more inefficient. Okay, good. So I guess this is what we'll be talking about in Monday. I will be going through the derivations and, some of these steps a little more closely.